Today we're going to finish up dynamic programming by finishing up the 0 and 1 knapsack problem, the dynamic programming solution to it, and then briefly introduce the other problem that we usually cover, optimal binary search trees. I'm not going to go into too much detail, simply because I have a whole video series on it with a much more detailed presentation with full pseudocode, full analysis, and all that stuff. So to continue with a 0-1 knapsack problem, what I want to do first is develop some, to codify what we did last time when we generated a solution. So remember that the main algorithm fills in this tableau, that the rows correspond to the elements A1, A2, A3, A4, and A5. And then these correspond to intermediate weight constraints. So initially you're considering that you can't carry anything. And then what if I could carry 1 pound? What if I could carry 2 pounds, ... What if I could carry 7 pounds, which is actually the input to this particular instance? Now, the way that we went about recreating the solution is we started down at the bottom right here. Remember that was the overall optimal solution, the value of the overall optimal solution, that the value was 19. And remember how we actually got that number. We looked at the one immediately above it, and then we looked at the one immediately above it, and to the left here somewhere, where we added the value of the fifth element here in this case. And then that decreased our weight capacity to somewhere over here. And there was some value over there. So probably, and unfortunately I don't have the one thing that we should, let's see. Let's go ahead and add that, add it back in, what the 0-1 knapsack input looked like. And it looks like I actually just wrote it down. So let me go ahead and go back and get that. All right. Remember the actual input to this was A1, A2, A3, A4, A5. It had weights 5, 2, 4, 2, and 3. These are weights, and these are the values: 10, 5, 8, 7, and 7. There we go. So we considered taking A5. And did we take it or not? Well, all we had to do was consider not taking it, corresponding to this, which had a value of 17. And then we had to consider actually taking it and seeing if it was feasible by going over 3 units, basically. 1, 2, 3. We're leaving us with a capacity of 12, right? Because to carry the fifth item would mean that we no longer have a capacity of 7. 7 minus 3 gives us a remaining capacity of 4. So 12 plus the value of 7 here, that's how we got 19. So we must have taken that in order to produce this value. Now, that can all be simplified by simply looking at the one right above it. Right? So we start out here, and we look at the one right above it, and we see that they're not equal. That implies that you took A5. And so we update, we go up, we add A5 to our basket, to our knapsack, whatever. And then we go up 1 level and then over 3, or whatever the weight of that particular item that we just took was. And so I'm going to go over here to this one, and I'm going to consider this, 12. I look above and I see that they're also not equal. And so I must have taken A4 as well. And so I will go 1 above. Did I take A3 or not? Remember my capacity has been reduced now. It was originally 7. By taking 5, it's now reduced to 4. By taking 4, it's now reduced by a further 2. So I go over here, and I consider this column right here. I look above it, and I see that they are equal. That implies that I did not take A3, right? So I did not take that one. And so I simply go up. I don't go over because I didn't take the element, and so my capacity is not changed. It's still 2. I am now at this level, and I look up and I see that they're not equal. That implies that I did take A3. or sorry, A2 is what we're on. At that point, my capacity is 0 and I can stop, or I can continue with this process as long as I don't go outside of this table. Once you hit the boundaries of this table, then you're done, right? That's what the solution that you've built. So let's go ahead and codify that as pseudocode, right? So my input will be a V, the value table of the 0, 1 dynamic knapsack algorithm. And my output will be a subset, the optimal, unoptimal solution S, right, of elements. In fact, I'll just go ahead and write that as a subset of the elements A1, A2, dot, 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 AN. Okay. So initially my knapsack, I could call it KS here, but I just called it S for sack, right? Sack, solution, whatever. Initially it's going to be an empty set. And then we're going to add things to it as we look at the table and see that we took that element. Okay, well, we didn't take that element, so I won't add it to the bag. I won't add it to the sack, etc. Note here that I am going to iterate on I, but I'm going to start at the bottom and move my way up here. So I'll start at N. If you're using 0 indexing, of course, you will have to update that. Where do I start my J? Remember, I'm using I and J here. I start my J at the other end because I'm going to start at this location. So I started at W. Right? And then I want to make sure that I'm not going to fall off the edge. So while I is greater than or equal to 0, or sorry, 1, why? Because once I get to 0, I'm done, right? There's no other item to consider here. I don't need to add anything to it. Greater than or equal to 1, and J is greater than or equal to 1. Why? Because once I get down to 0 for J, then my weight is done, right? I'm going to do another while loop inside here, and I'll explain why in a second. While I is greater than or equal to 1, and V sub ij is equal to V sub I minus 1j. Right? That loop is going to take me up, right? As long as these two things are equal, right? Let's look at this column here. This is equal, equal, right? As long as it's equal to the one right above it, I keep moving up because I did not take that element, right? So I plus plus, right? Now, why did I include this here? Well, because you could. It is possible to get stuck in the middle of the table and then go all the way up and then exceed the bounds of this table. I just want to make sure that I take care of that in both the outer loop and the inner loop. Okay. There we go. Otherwise, once they're not equal, once I've broken out of this inner for loop here, I know that either it's going to be 0, in which case you can break out of that, or oh, sorry, what am I doing? We're moving up, so oops, minus minus. There we go. Once I've broken out of this for loop, that means that I'm taking that current item there. Okay, so I will update my S to be S, and then I'm adding the ith element here. There we go. Yep. Now, what I need to do is I need to continue. Once I've taken that element, I move up 1, and then but I also move J over by some value, right? So I is going to get a minus minus, but J is going to actually jump over several columns depending on the weight of that particular item, right? And that's just simply, here we go, J minus W sub I, the weight of the ith element that you just took by adding it to your solution, right? There we go. And that's the end of my outer loop, and then output S in the end. And that's it. Okay, so what is the complexity of all this stuff? Right? Well, it should be pretty clear that when you're creating that table, right, that filling out the table is simply order NW, right, where N is the number of items and W is the weight capacity. Right? I will note here that building a solution can be done in order N, right? Because remember that we are only going up, up. Sometimes we take that item and then we jump over here, but we're not going to look at the entire table. We're only going to iterate, basically asking, should I take this item or not? Should I take this item or not? Should I take this item or not? And there are only n items, so it's going to be order n, right? That's not the important part. So if we assume that W is a constant, is the complexity linear? Right. Well, from that point of view, yes. So can you assume that W is a constant? No. The 0-1 knapsack problem is an NP-complete problem, meaning that it is very, very difficult to solve. Only exponential time algorithms are known to solve NP-complete problems. This is something that we'll get into here starting tomorrow. So why does it look like it's linear? This is usually what's referred to as pseudo-linear. Pseudo-linear, right? The analysis is hiding the true complexity by ignoring W, right? It could be pseudo-linear. Hopefully that's not, okay, that's not a word according to my spell checker, but it is a word used. It's a term of art. It is used. It could be that W is going to be order 2 to the n. Right? And this gets into parameterized complexity, something I don't want to get into right now. But basically, your input, if there are n elements in there, then it takes a certain number of bits to represent those n elements. It also takes a certain number of bits to represent the values. It also takes a certain number of bits to represent the weights, right? And the weight capacity. Since there are n elements, you have an additional n or polynomial number in n bits to work with in order to represent the weights, and you're not changing the input size at all. It's still within a polynomial of the original n. If you have a polynomial number of bits, let's just say that you have n bits, right? So suppose you have n bits to represent W. What is the maximum value? I mean, again, you can have like n squared or n cubed bits, or if you really want to, any polynomial number of bits, but n bits is enough to illustrate what I'm going to show you here. Suppose that you have n bits to represent W. Then W could be as large as 2 to the W. Right? Why? Well, because of the way bit representation works, right? If you have x, how many bits does it take to represent x? Log x. Going in the other direction, if you have n, how many bits to work with? What's the largest number that you can represent as an unsigned integer or a integer or whatever? It's going to be about 2 to the n. 2 to the n minus 1, and then 2 to the n, or sorry, not 2 to the w. What am I writing here? It could be as large as 2 to the n minus 1, technically. 2 to the n minus 1 if you need a bit for the actual sign, but we'll assume that we have a non-negative weight value because, you know, if you have a knapsack that you can't, that has a negative capacity, that means you can't take anything, right? And so that would be a trivial instance. But if you have that many bits to represent it, then it could be as large as 2 to the n. Consequently, your tableau would be exponentially sized. And to fill out that tableau means that you would be filling out a 2 by 2 to the n tableau that kills you for your runtime. Okay. So we did not solve the P versus NP problem. If you're familiar with that, you will be shortly after we get done with complexity in this course. Okay. Remember, we are on Piazza. We are on YouTube. If you have any questions, go ahead and post there. But otherwise, I'm going to introduce, again, not go over in great amount of detail because I already have a pre-prepared video series on it. The next problem, it's optimal binary search trees. Right? So given a set of keys and a probability distribution of searching those keys, I want to create the optimal binary search tree. Right? Now, what do we mean by optimal? We mean that we know how many times we're going to search for a particular key, and so we don't want a balanced tree anymore. What we want to do is we want to make sure that high-value targets are shallower in the tree, so that it takes a fewer number of comparisons to find them. So to illustrate what I'm talking about here, I'm going to go ahead and give you an example. Let's see. This is a very small example, right? So suppose that there's this key distribution. Here are my keys, A, B, and C. And I don't know what these are. Who cares? It doesn't matter. But just know that A is less. We're going in lexicographic order here. A is less than B. B is less than C. Okay. So any binary search tree has to have A as, there are a couple of possibilities here that we'll get into in a second. But otherwise, it has to respect that order. It's still going to be a binary search tree. Okay. Suppose that I've got probabilities here, right? And again, this is the probability of searching for key K, right? This can be empirically measured. This could be guesstimated and then adjusted as needed or something like that. But just to show you what I'm talking about here, let's suppose that we have the following distribution, right? Now the interpretation here is that 60% of the time we search for A, right? 30% of the time we search for B. And only 10% of the time we search for C. Right? So some searches are more common than others. Now the application here is that we know this up front. We know all the keys up front. We know the probability, a priori the probability of searching for those keys, or at least we have a good estimate on it. This particular application means that we're not going to be inserting a keys because that would disrupt the probability distribution. We're not going to be deleting keys. We're just going to be searching for keys. So I want to build the best possible tree. If I'm naive about it and I don't take the probabilities into account and I just make a balanced tree, for example, then what is my expected number of comparisons to search throughout this tree? It's kind of like Huffman coding when you did Huffman coding. What is the expected or the average code word length? So for this particular example, where we've got a balanced tree, to search for A would cost me how many comparisons? Well, I would have to come and search for B, find that that's not the thing that I'm looking for, go down to the left child, compare to A, and find that that is the thing that I'm looking for, right? What about searching for B? Well, since it's at the root, I only need one comparison. And so searching for C, it's symmetric, so of course it would cost me two comparisons. But now that we know a probability distribution on this, we can say, well, we're doing this first search 60% of the time. We're doing the second search 30% of the time, and this last search we're only doing that 10% of the time. So if I summed all of these up, then I would get the expected number of comparisons to search for this tree, to search through this tree for any particular key. And that's going to be 1.7. Yep, there we go. There. All right, well, that looks okay, right? It's definitely less than 2, but can we do better? let's go ahead and look at another configuration here. What if I skewed it? What if I put A at the root, knowing that, oh, well, that's the most common thing that I'm going to be searching for, so I'll go ahead and put it at the top. I'll be greedy about it, okay? And then I went and put, I don't know, now B and C both have to be over here as a subtree. All right, it still has to be a binary search tree. So I can't just put C and B and C over here because that would violate the binary search tree property. Right? So what do I put here as my new root between B and C? B or C? Which one do I put? Let's go ahead and try C first. Now, once I've made that choice, the last choice is made for me. B has to be a left child of C. Okay? Did I do any better? Well, now it only costs me one comparison to search for A. It costs me 3 comparisons to search for B and 2 for C. Again, for B, why? 1, to find out that that's not the thing you're looking for. 2, and then finally 3. You've found it. Basically, it's the height or the depth of the nodes. Okay? So, this if I take the probability distribution into account, this is going to be 0.30 and 0.10. There we go. And I come up with I think the exact same answer, 1.7, right? So even though it's skewed now, right? In fact, if this were an AVL tree, it would definitely come up with a right-left rotation to fix the skew. Then it would be bad because it's skewed. But it's no worse than the balanced binary search tree, than the balanced tree that we started with. Okay? Can we do even better? Well, I still want A, say, as my root, because now intuitively I'm just being greedy here. We'll put the most common things first. And a super skewed tree all the way to the right. Now it's going to be number of comparisons is 1, 2, and 3. And when I multiply that by 0.6, 0.3, and 0.1, right, I do get a better, on average, number of key comparisons, 1.5. Now, I was just being greedy about this, but you can come up with counterexamples where if you're greedy about it, then it will not lead to an optimal solution. Instead, what I need to do is I need to bring dynamic programming to bear here. Okay? All right, still no questions online. But how many other possibilities were there, by the way? Right? At least for a 3-node tree? Well, there's a balanced one. Right? There's the one that's skewed completely to the right. These are the ones that we just considered. There's one that's skewed to the right and then to the left. And then there's all the symmetry out of this. Skewed completely to the left, skewed to the left, and then to the right. Right? There are 5 possibilities here. Right? That's in fact that corresponds to a balanced tree, a right-left rotation, a right-left rotation, a right rotation, and finally a left-right rotation in an AVL tree. But in general, if I have n keys, the number of possible binary search tree configurations is huge. In fact, it corresponds to these things called the Catalan numbers. Right? You may or may not have seen that when you took a course on combinatorics. But it looks like something like this. So 1 divided by n plus 1, that's inconsequential. But 2n, choose n. Now, if you remember back, twice now we've covered binomial coefficients and noted that they are maximized when you're choosing about half as many as the values of the values that you actually have. If you were to actually write this out, you can go ahead and say that this is 2n factorial. The denominator does not make a dent in trying to eliminate this. This is n plus 1 over n factorial. Right? When you start canceling these things out, you will still have 2n minus 1, 2n minus 2, all multiplied together. It's huge, right? In fact, you can show that this is going to be order 4 to the n. I think using Stirling's formula or something like that, with some polynomial factor under here. Who cares? Exponential. Okay. So there's no way that we can do this brute force. Instead, we need to bring dynamic programming down to bear here. For that, what I'll do is I will show you a picture. And again, we're accelerating this. If you want the full presentation, take a look at the pre-prepared YouTube videos. Let's see. There we go. All right. So let me set this picture up. So given keys K1, actually, yeah, let me move this picture. Oops, come on. Let me move this picture off for a second here. Given keys K1, K2, ... Kn. The question that I want to ask in the small is, which one of these should be the root of the tree? Which K sub L should be the root? Right? Just like I did over here, right? Well, what if I made A the root? Then I could have a configuration down here. What if I made B the root? Then I could have a configuration over here and a configuration over here. What if I made C the root? Then I would have a couple of other configurations to consider, right? So let's go ahead and say that we select keep it general KL, right? That I go K1, K2, ... KL minus 1. This is my lucky guy right here. Right? That's the lucky one that that turns out to be optimal. That's my optimal choice. What I'm going to have to do now is recurse and ask the question for, well, what about these keys? And what about these keys? Right? And so that'll lead to a configuration that looks something like this. I'm just going to go ahead and shove all those keys into one tree, because they have to be, because it's a binary search tree, and all these keys come before this key. You have to put them in as children somewhere in the left subtree. So K1 through KL minus 1, and hanging off of this will end up being KL plus 1 through KN. Right? Now that's just for the first iteration. In general, I'm going to have some subset of those keys. Right? Now it's not necessarily a subset, it's a subsequence of those keys, because they're all contiguous. Because K1, K2, K3, they're all in order. When you go to program this, of course, you're going to have to sort it, because that's the proper order, right? Ultimately, what you have is, in general, I should say, is something that looks like this, right? Where you have, oops, okay, I'll go ahead and go to the next one. Fine. Optimal binary search tree. There we go. All right. Ultimately, what you have is keys K1, or Ki, excuse me, through Kj. And then you consider, well, what if I made the first key the root? That would lead to an empty tree over here and all the other keys being over here. What if I made the second key the root? What if I made the third key the root? ... And then among all those possibilities, you're going to consider I plus 1, ... KL minus 1, KL, KL plus 1, ... KJ. You're going to consider making all of those keys a root. And then you are going to pick the best one, right? The one that minimizes the number of expected key values, key comparisons to search the tree. Right? What does that look like? So C sub ij, I'll make that into the number of expected comparisons. Right? This is the optimal number of comparisons for keys Ki through Kj. Right? We're not going to use K anywhere here because we've already used that as our key. Right? We're not going to use that as an index value. Right? So all you have to do is consider splitting it at each one of those things. Split it at I, split it at I plus 1, split it at I plus 2, ... split it at ij, or at j. So you're going to take the minimum among all those values, starting at I, and here that's why I'm using L here, up to and including j. Right? And you're going to split it at I up to L minus 1 plus L plus 1 J. Right? Now, I've excluded L, a case of L in this case, but we do have to keep track of it, right? Or that we do have to consider it, right? By making KL our root, I'm necessarily putting everything else over here and necessarily putting everything else over here. In other words, I'm necessarily increasing the size of my tree. That's going to cost me something, right? That's going to cost me a sum of probabilities. And here I'll use yet another variable, S. There we go. For S, going from I up to J. Right? Now, you'll note here that this is actually invariant. It does not depend on L, right? I'm summing up all the probabilities of all of these keys. And why? Because there's a 1 sitting out front here. 1 times the probability. Because I'm increasing the size of the tree, meaning that I'm adding one more comparison for all of these nodes in the trees. Because I'm necessarily making it lower, and so to even get there, I need one more key comparison. Whatever key comparisons are over here, they're one less as well because I've built up this tree from above. Right? So again, I'll annotate this. This is the cost of increasing the depth of the optimal binary search tree. Right? This is the optimal cost of keys ki through kl minus 1. And this one is the optimal cost of keys k sub l plus 1 through k sub j. All right? And again, you are iterating over all possibilities. Okay? We're not going to go into the proof that this is correct, and we're not. And you can imagine also the base cases, right? That if there's just a single node, right, C sub I, that's just going to be the probability of K sub I, right? The probability of searching for that one key because you're considering a one node tree, right? It's going to take you one key comparison to say, is that the thing I'm looking for or not? And you know, you ask that question and you get your answer, and that's all it costs you, right? One comparison times the probability of searching for that key, but that's why we don't write 1, right? There we go. And of course, you've got other values here. C sub I, J for is going to be 0 for J greater than I, right? Why? Because it's an empty tree. Your keys, you know, I've got I and J. When those two things pass, I'm no longer when they meet, then I'm considering one node tree. When they pass each other, I'm considering no keys at all. Right? Okay, that leads to the next step in the process. Come up with a table and figure out how to fill it out. And that's the one that I'm going to skip the details on and just show you the final picture. Here we go. There. Right. So you're going to set this up as a matrix. This is I plus 1, ... This is all the way up to n plus 1, n, and then n plus 1 down here. Right. And then 0, this is I and j. 0, 1, 2, or ... Oops. ... all the way up to n over here. Right? I guess it starts over here, 1, 2, ... Right? There are going to be a lot of invalid things, right? If you are considering keys that come after these keys over here, then there's going to be an invalid section, just like there was for the binomial coefficients. You can initialize all of these to 0 if you want to, right? Or you can just skip them by writing a proper loop. I cover the proper loop in that video series. All right. Now, how does it actually work here? And it's much more complicated than what we looked at before with either the 0, 1 knapsack or the binomials. The binomials, in both of those cases, you only had to look at the one row right above it. But as these arrows imply, it's much more complicated here. Because you're splitting at, say, I minus 1, then you're taking this value and then you're comparing it to this value over here. You're not comparing it, but you're taking this value and adding it to this value over here. A second split on the second key is going to correspond to this one, and then you compare it to the second one, the next one down in the row over here. You can look at all of these comparisons, and then you take the minimum one, and that gives you your answer for C sub ij. Now, clearly, what we want is keys 1 through n. So it's this last one up here that gives us the ultimate answer. Not only that, but like Floyd-Varshall's algorithm and Dijkstra's algorithm, where we kept track of the optimal solution, we also kept track of a bunch of other artifacts that allowed us to rebuild that optimal solution. Okay? So how does that work with respect to optimal binary search trees? Again, I give full pseudocode in that video series. I will just give you the idea here. Here's one particular example. Okay. This particular example was, A, B, C, D, and E. This does not correspond to a key here. It's just there so that you have this extra 0, right? So that when you're checking for a bounds for this one, you have these two numbers to compare, right? Again, you can fill this out with zeros or you can ignore it. This is the final solution here, where the average number of key comparisons is 1.573, right? And in the videos, I go over an example of how to calculate a few of these things. I don't want to do that a lot because 5 times 5 times 5, 125 possible combinations here. Not exactly that many, since you're not considering all the keys at all times, but it's just plugging and chugging, right? It's not that important. And of course, this corresponds to A, B, C, and D, E. So I want to know, and this, what is the optimal binary search tree that gives me keys A through E here? Okay. What I do is I keep track of the value that gave me that optimal solution. So let's go back over here. I keep track of the L that gave me the min, right? And I put that into this table over here. This is called a root table. If I look up the values of keys 1 through 5, which correspond to A through E, then this entry will tell me that 3 gave me this value over here. So all I need to do is build the tree starting at 3, which corresponds to C. All right. Now, over here in the left subtree, I still have A and B. I don't know what the configuration of that is yet. Right. Over here, I have a configuration including D and E. Right. My next question is, what is the root of this tree and what is the root of this tree? Again, I go to my root table. The root of this tree involves keys A through B, which correspond to 1 through 2. And it tells me that 1, or A, should be my root. Right, so let me go ahead and build that now. At which point I have no choice on where to put B because, of course, it has to be a binary search tree. But, of course, you can't just tell a dumb computer you have no choice. There's only one. Computer's not going to figure that out. So I ask the question of, well, I don't put it over here. This is going to be empty, right? That corresponds to, say, like 2 through 1, 2 through 1, and you see immediately that it's empty, and so there's no left child. What about my right child? Well, that's 2 through 2, which it was initialized to 2. In fact, look at this diagonal here. 1, 2, 3, 4, 5. A single node tree is always going to be its own root. So that's why we have 1, 2, 3, 4, 5. And consequently, B becomes the right child of C. We're going to look at an extended example here in a moment. What about D through E? D through E. It tells me that E should be the root. Right. And then, of course, I have no choice for D but I would still do a lookup for it because D through D says that D should be the root. Right? And that is going to be the optimal binary search tree with that key. I didn't give the key distribution. It's in the notes if you want to, but it comes up with this number. Right? I just threw numbers out there, I think. Right? Okay, great. So how do you go about filling out the table? How do you go about building this tree? Full pseudocode is available both in the notes and in the pre-prepared video series. What I want to do with the remainder of our time here is get a little bit more practice. And again, every Friday, usually we have a quiz, but I'm going to go ahead and do that early by giving you a quiz and a test. So here's an example. Consider the binary search tree below, which contains search items for sports. So some of these sports are more popular than others and therefore are searched more often. Baseball has a 40% probability because it's much more popular than football. I wish. Monetarily, that's not true, but I don't know about actual number of viewers. Hockey is unfortunately down there. Shinty and Shirling, one of those is real. One of those is fake. If you want to do some Google searching to find out what they are, go ahead. But I went ahead and created this binary search tree. It is a binary search tree because it is, B, F, and H are all less than S, and then SHIN is less than SHIR, so it's in lexicographic order. It is a binary search tree. But what is the expected number of key comparisons made by this tree? Okay, so all you need to do is look at the depth of each one of these things. Unfortunately, I never bothered to bring this over, so we're going to have to go back and forth on this. But Shinty is going to take one comparison, so key, number comparisons, and the probability distribution. Remember that Shinty was 4%, so 0.04. Going back over here to the binary search tree, football is going to take 2 because you start at Shinty here, go down to the left child, and find football. Again, it's just the depth of these things. Baseball and hockey are both 3. And then likewise, Shirling is 2. Right? And I'm going to go ahead and fill in the probabilities for each one of these as well. 35%, 0.35. Baseball is 0.40. Hockey is 0.13. And 0.08. Right? At this point, it's just plug and chug. But you multiply each one of these together, you add them all up, and you get your answer. Right? I trust you can use a calculator, so we're not going to go into that. But I wanted to show you the process with a larger tree. Okay? All right. Mark each as true or false. You need not give any justification. Because the dynamic programming solution for the 0-1 knapsack problem is order NW, the problem is solvable in polynomial time. That is false. That is pseudo-polynomial time. Floyd's algorithm can be used to find the shortest path between any two vertices in a graph. That is true. What if I change that question? Can Dijkstra's algorithm be used to find the shortest path between any two vertices in a graph? Yes, you just have to set one of them to be the source, right? Both of those are shortest distance. Remember, the difference is that Floyd's, with one run of Floyd's, you get all pairs shortest paths. With one run of Dijkstra's, you only get a single source shortest path. You'd have to run Dijkstra's over and over again n times in order to get the shortest distance between any two nodes in a directed graph. Right? A heap allows you to find a median element in order 1 time. Definitely not. A heap only allows you to find the minimum, put stuff in, find the minimum, change the priority in order log n time. Right? A heap can be used as an efficient implementation of a priority queue. That is true. That's its primary use. A minimum spanning tree of graph G is unique. That's false. Of course, you can come up with several of them. Right? That was the quiz. All right, it was short. I cut one of the questions out. But here is the final from a couple of summers ago, and I'm only going to go over the binary search tree, optimal binary search tree section here. So suppose that T is an optimal binary search tree with n keys. What is the maximum depth of T? Okay. So there is no. We're not talking about balance here. This is asking. This question was designed to ask you: did you understand why we did optimal binary search trees? It's not necessarily going to be the most balanced tree. It could be that it's skewed, right? You could come up with a probability distribution where this ends up a completely skewed tree ends up being the optimal tree. And in this case, what's the depth? Well, there are 1, 2, 3, 4, 5 nodes, and the depth is 1, 2, 3, 4. So in general, if you've got n nodes, the depth could be maximized at n minus 1. Right? Suppose that we have 7 keys, and we want to create an optimal binary search tree, but the probabilities are uniform. That is, each key has a probability 1 over 7, right? Whatever percentage that comes out to. What would the tree look like, and what would be its depth? So if you have a uniform distribution, then that means that you can be greedy, right? That you can go ahead and put these 7 nodes in a full tree of depth 2, and that's going to end up being the optimal. If you don't do that, then it's going to be skewed either to the left or to the right. Right? And once it's skewed, that necessarily increases the height or the depth with respect to the tree itself, the root node. Those are the same things. When you increase the height or the depth, yeah, you might get by over here, but then it's going to be deeper over here necessarily. Now there might be some equivalent binary search trees that don't optimal binary search trees that don't look that can be a bit skewed, but otherwise the easy answer here is just to make it into a if it's uniform probability, there's no reason to prefer one node or over another. Just make it into a full binary search tree with the keys ordered properly. Right? Okay. The last one. I might actually, give me a second here since we have time. Let me take a screenshot of this. There we go. And bring it over to the tablet. Bear with me. Oh, wow. Hopefully. There we go. Hopefully I'll be able to do this and it doesn't grind everything to a halt. Okay. All right, let me try that one more time. Take a screenshot of this. All right, not gonna do it. That's all right. Okay, at least it's not grinding everything to a halt here. So what we're going to do is we're going to look at keys 1 through 8. Now, it's not 1, 2, 3, 4, 5, 6, 7, 8. The keys correspond to these numbers up here. So if I consider the first one, 21 through 93, which are indexed 1 through 8, then I look at this value right here. And so 52 is going to end up being my first node, my first root node. Let's see if it has successfully done it. Yay. All right. Now I don't have to keep going back and forth if I take this screenshot over here. There we go. And it's not showing up because iCloud is extremely slow. Don't try to run OBS and iCloud at the same time, apparently. Nope. All right, so I'm going to have to go back and forth. Sorry. All right, so now, how do we determine what's in the left subtree and the right subtree? 52 is this key here. So basically, I'm looking at keys 1, 2, 3, 4. what is the optimal root node for 1 through 4? And I look at this table and I see 1 through 4, it's 21. So with me, go ahead and write 21 as the left child of 52. Likewise, 52, I've got 72, 76, and 93 as its right in its right subtree. So what that corresponds to 6 through 8. So I look 6 through 8, and I see 93. And if you're following along with me, your tree should look like this so far. Okay. And let's try it one more time, see if iCloud has updated. There we go. There, now I don't have to go back and forth. All right. And I can draw your attention to the actual numbers. All right. Okay. And remember the keys are 21, 33, 35, 38, 52, 72. I should have left myself some more room. I can do that with magic. Put it over here instead. 72, 76, and 93. And remember, these are indexed 1, 2, 3, 4, 5, 6, 7, and 8. Okay. So I've built this tree so far. Now, 21, so this ended up being my root, main root. This ended up being my root of the left child. And so now I need to determine what is the right child of 21. So I look through 2 through 4. Right? 2 through 4. And it tells me 35 should be the right child. There we go. You'll note here that the left child is empty because I've already fallen off my key, the number of keys that I have here. Okay, and you'll also note here that once I put 35 in there, then 38 and 33 are pretty much determined. All you need to look at is 2 through 2 gives you 33, 4 through 4 gives you 38. Right? So 33 and 38. Okay. Continuing on the right subtree, rooted at 93, these two, so the right subtree is empty because there is no 9, 9. You're already outside the table here. Remember, this is the root table, not the actual optimal table, the optimal value table. So I'm going to have 72 and 76 as left children of 93. Which one is the root? I look at 6, 7, and I get that 76 should be the root. And then, of course, 72 ends up being completely determined there because it's alone. If you look at 6, 6, then 72 is the new root there. Okay. All right. Still have a little bit of time. Let me check the rest of the quiz, or the rest of the final, I guess. All right. Now, we'll go ahead and save that for the final review. There are lots and lots of other dynamic programming problems that you can cover and look at. Once you've seen 2 or 3 like we have, they all start to look the same. It's the same basic process. You come up with a recurrence, you come up with a tableau, you figure out how the tableau needs to be filled out, you keep track of any information that's necessary for building the solution back up. And in fact, the other two that we can look at would be matrix chain multiplication and change, like the dynamic change making algorithm. They're basically almost virtually identical. In fact, the optimal matrix chain multiplication is identical because it corresponds to the Catlin numbers as well. That for the idea there is that you've got a bunch of matrices that you need to multiply together. Multiplying certain matrices first will reduce the number of entries and reduce the overall number of multiplications necessary to get the job done. So you shouldn't just go left to right, right? That would be greedy and naive. Instead, you can multiply these two, then these two, then these two, then these two, and then start combining them together. And so doing that basically is, well, which two do I do first? I do these two first. That's basically like splitting it out into 2 problems. And once you've got the solution to both of those problems, you multiply them together, right? Well, what is that? That's an evaluation tree. which is a binary tree. And it's just a different criteria for which where you split the tree. Instead of a bunch of keys and the optimal key split, you're looking at the optimal multiplication split. So they're all pretty much the same, which is why I don't like to go over problem after problem after problem. Once you've seen 2 or 3 of them, then you can pretty much get the idea of how it works. If you have questions, I do cover 0, 1 knapsack and optimal binary search trees, because those are options for you to implement in your final assignment. There is a third one that I didn't cover. It's the largest non-contiguous palindrome problem that lends itself to a dynamic programming solution. You can go ahead and check that out and ask questions about it during office hours or on Piazza. But otherwise, tomorrow we will start on the next and last module, which is going to be structural complexity, not just big O complexity, but we're going to talk about computational models, limitations of computational models, and P and NP completeness. Okay, I'll see you in office hours then if you need help. Have a good day.